Welcome to The Chill Scientist. This is part 2 of black holes. Check out part 1 to understand this much better. The term holographic principle was introduced in the 1990s by Gerard 't Hooft and Leonard Susskind, who argued that the maximum entropy that can fit in a given region of space is proportional to its surface area, not its volume. If you try to pack more information into that space than the area allows, gravity takes over and a black hole forms, erasing the extra detail. This sets a universal limit on how much information the universe can hold. In simple terms, the principle states that all the information describing a region of space can be fully represented by data stored on its boundary. The volume is redundant. Everything happening inside is encoded on the edges. It's a shocking concept because it means that the true fabric of reality might be two-dimensional, with the third dimension emerging as an illusion from the underlying information. The idea gained real mathematical footing in 1997 when physicist Juan Maldacena discovered a precise example of it in string theory known as the ADS/CFT correspondence. In this model, a universe with gravity existing in a higher dimensional bulk, specifically anti-de Sitter space, is exactly equivalent to a quantum field theory, without gravity living on the lower dimensional boundary of that space. Every event in the bulk has a corresponding description on the boundary, and vice versa. The two theories, one gravitational, one quantum, are mathematically identical. Although our universe isn't an anti-de Sitter space, the correspondence provided a powerful proof of concept. Gravity and space-time can emerge from purely quantum, lower-dimensional systems. Since then, physicists have used the holographic principle as a framework for studying black holes, quantum gravity, and even condensed matter systems. It offers a bridge between relativity and quantum mechanics, showing how gravity might arise from quantum information itself. In this picture, space-time isn't a static stage, but a manifestation of quantum entanglement, the invisible connections between particles that share information instantaneously. According to recent theoretical work, the geometry of space may literally be built from patterns of entanglement. The more entangled two regions are, the closer they appear in space. Break the entanglement, and space itself begins to tear apart. This is a profound shift in how physicists think about reality. The holographic view also reframes the black hole information paradox. If everything inside a black hole is encoded on its surface, then information isn't truly lost when matter crosses the event horizon. It's just stored in a different form. As the black hole radiates and evaporates, the information can, in principle, be recovered from correlations in the outgoing radiation. The destruction of information might be an illusion caused by our limited, three-dimensional perspective. Beyond black holes, the holographic principle hints at a universal limit to information density, sometimes called the Bekenstein bound. It means there's a maximum number of bits that can be stored in any given region of space before it collapses into a black hole. For a 1 meter cube, about 3.3 feet, that number is around 106,910 to the 69th power 169 bits. No physical system can contain more information than that without triggering gravitational collapse. This limit ties information theory, quantum mechanics, and gravity together in a single framework. It implies that information is not just an abstract concept, it's a physical quantity as fundamental as mass or energy. Every bit of data has weight, every calculation requires energy, and every attempt to compress information beyond a certain threshold warps space-time itself. In cosmology, the holographic principle has been used to interpret the entire universe as a kind of cosmic hologram. The observable universe may correspond to data stored on a distant cosmic boundary, perhaps the edge of space-time itself, known as the cosmological horizon. Some versions of the theory even suggest that our universe's expansion and structure might be governed by the flow of information across that boundary. While the holographic principle remains theoretical, it's supported by consistent mathematics and by the behavior of black holes, which obey the area entropy law to remarkable precision. Experimental verification is challenging because the scales involved are beyond direct reach. Still, researchers are finding analogs in laboratory systems, condensed matter materials, quantum computers, and even fluid dynamics, where holographic-like behavior appears. If the principle is true, it represents a fundamental change in how we understand existence. Reality as we experience it, the space we move through, the matter we interact with, and even the flow of time may be a kind of projection. The universe could be a vast, self-organizing information system, with space-time and gravity emerging from deeper quantum correlations. In that view, black holes aren't exotic exceptions. They're the rule made visible, nature's clearest expression of how information, energy, and geometry are woven together. The holographic principle suggests that what we call space is a construct, and what we call information is the foundation on which everything else rests. The origin of the first black holes is one of the central mysteries in cosmology. We know that supermassive black holes, millions to billions of times the mass of the Sun, already existed when the universe was less than 1 billion years old. We can observe them today as quasars, bright beacons of radiation from the early cosmos. But their existence so early poses a problem. How could something so massive have formed in such a short time when the universe itself was still in its infancy? To understand this, we need to go back to the beginning, to the period just after the Big Bang, when the first stars and galaxies were forming. About 400,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine into neutral hydrogen. Light could finally travel freely, creating what we now observe as the cosmic microwave background. Over the next few 100 million years, gravity began pulling matter together into denser regions, forming the first stars, known as population 3 stars. These early stars were very different from those we see today. Composed almost entirely of hydrogen and helium, they lacked the heavier elements that help cool modern stellar gas. As a result, they were massive, often hundreds of times the Sun's mass, and short-lived, burning their fuel in just a few million years. When they died, their cores collapsed, forming black holes with masses between about 30 and 300 times that of the Sun. These stellar black holes were likely the seeds from which larger ones grew. They could have merged with other black holes, accreted gas from their surroundings, and increased in mass over time. But even with efficient accretion, it's difficult for such small seeds to grow into billion solar mass giants in less than 1 billion years. The process would require nearly continuous feeding at or above the so-called Eddington limit, the maximum rate at which radiation pressure and gravity balance. Sustaining that growth for hundreds of millions of years is hard to explain. That puzzle has led to alternative theories. One idea is that some black holes formed directly from the collapse of massive clouds of primordial gas, bypassing the stellar phase entirely. These direct collapse black holes could have started with masses of 10,000 to 100,000 suns, giving them a significant head start toward becoming supermassive. Conditions in the early universe may have favored such collapses. In particular, regions with strong ultraviolet radiation that prevented the gas from fragmenting into smaller stars. Another possibility is that dense star clusters at the centers of early galaxies merged their contents rapidly, creating a single, extremely massive black hole through runaway collisions. In this scenario, stars collide and merge faster than they can explode as supernovae, leading to a giant core that collapses directly into a black hole. Some researchers even speculate about primordial black holes, objects that might have formed during the first fractions of a second after the Big Bang, from density fluctuations in the hot, dense early universe itself. These would predate stars entirely. Depending on their size, Some could have evaporated long ago through Hawking radiation, while others might still exist today, contributing to dark matter. Although evidence for primordial black holes is still lacking, they remain a serious theoretical possibility. Once black holes began to form, they played a major role in shaping cosmic structure. As early galaxies assembled, their central black holes grew rapidly by accreting gas and merging with others during galaxy collisions. The energy released by this accretion process affected their surroundings dramatically. Radiation and outflows from active galactic nuclei heated and dispersed gas, regulating star formation and influencing how galaxies evolved. Simulations of galaxy formation consistently show that including black hole feedback, the injection of energy from accretion and jets, is necessary to reproduce the observed universe. Without it, galaxies grow too large and too bright. With it, they match the distributions we see through telescopes. The evidence suggests that galaxies and black holes co-evolved from the beginning, locked in a feedback loop that balanced their growth. Observations of distant quasars offer direct snapshots of this process. The light we see from these ancient objects began its journey billions of years ago, allowing us to look back in time. Many of the brightest quasars discovered by surveys such as the Sloan Digital Sky Survey or the James Webb Space Telescope are powered by black holes already containing billions of solar masses just 700 million years after the Big Bang. Their accretion disks shine across vast distances, outshining their host galaxies and serving as cosmic lighthouses from the era of ionization. The period when the first light sources ionized the intergalactic medium. Recent discoveries by the James Webb Space Telescope have added more complexity. Webb has identified galaxies and possible black hole candidates at redshifts higher than 10. Corresponding to just a few 100 million years after the Big Bang, these objects are surprisingly massive, suggesting that black hole formation began even earlier than expected. If confirmed, it would imply that the universe wasted no time in creating its first gravitational giants. Supermassive black holes in the early universe also likely helped reionize the cosmos. As their accretion disks emitted intense ultraviolet and X-ray radiation, they stripped electrons from hydrogen atoms in the intergalactic gas, turning the opaque early universe into the transparent one we observe today. In this way, black holes weren't just products of cosmic evolution, they were agents of it. Over billions of years, these early seeds grew and merged, eventually becoming the central black holes in the galaxies we see around us today. The one at the heart of the Milky Way, Sagittarius, a star, is relatively modest, with about 4 million solar masses, but others have reached staggering sizes. The largest known, Tian 618, has an estimated mass of over 60 billion suns and a disk so luminous that it can be seen from over 10 billion light years away. The growth of black holes tracks the history of the universe itself, from the collapse of the first stars to the complex, structured cosmos we inhabit now. They are both the fossils and the architects of cosmic evolution, marking the key moments when matter condensed, galaxies formed, and the universe took on its present form. In the modern universe, supermassive black holes continue to shape the galaxies that host them, even though they occupy only a tiny fraction of a galaxy's total volume. Their influence reaches far beyond their immediate surroundings. The energy they release through accretion, jets, and radiation regulates how galaxies grow, form stars, and evolve over billions of years. At the heart of nearly every large galaxy sits a central black hole, ranging from millions to billions of times the mass of the Sun. When these black holes are actively feeding, consuming gas and dust drawn toward the galactic center, they become the engines behind active galactic nuclei, or AGN. Depending on their brightness and viewing angle, they may appear as quasars, Seyfert galaxies, or radio galaxies. Though their appearances vary, the underlying mechanism is the same: gravitational energy converted into radiation as matter spirals inward. The energy output from an active nucleus can exceed that of all the stars in the host galaxy combined. This radiation doesn't simply escape into space, it interacts with the surrounding gas, heating and expelling it in massive outflows. Observations show that these outflows can reach velocities of several thousand kilometers per second, several million miles per hour, enough to drive gas out of the galaxy entirely. These feedback processes are crucial in explaining why galaxies look the way they do today. Without them, gas would continue to cool and collapse into stars indefinitely, leading to galaxies far more massive and bright than what we observe. The energy from a black hole acts like a regulator or cosmic thermostat, preventing runaway star formation. In massive galaxies, this feedback keeps much of the gas hot and diffuse, halting new star births and leaving behind older, redder populations of stars. Astronomers see this effect clearly in elliptical galaxies, which tend to host the most massive black holes. Many of these galaxies show evidence of past AGN activity, cavities in their surrounding gas, shock waves, and vast bubbles of hot plasma. In galaxy clusters where dozens or hundreds of galaxies reside, the central supermassive black hole can heat and stir the cluster's intragalactic medium, influencing an entire region millions of light years across. The Milky Way provides a quieter but still instructive example. Sagittarius, a star, our central black hole, is currently in a low activity state, but evidence suggests it was much more active in the past. Observations from X-ray and gamma-ray telescopes have revealed giant lobes of high-energy emission, the so-called Fermi bubbles, extending tens of thousands of light years above and below the galactic plane. These structures likely formed from powerful outbursts millions of years ago, when Sagittarius A star was actively accreting material and launching jets. Even in its calm state, Sagittarius, a star, affects the orbits of nearby stars. Astronomers have tracked these stars for decades, watching them whip around the invisible mass at incredible speeds. The star S2, for instance, completes an orbit every 16 years and reaches speeds over 7,500 kilometers per second, about 4,600 miles per second, at its closest approach. These observations provided the most direct measurement of the black hole's mass and offered a test of general relativity in a strong gravitational field. When galaxies collide, a common event over cosmic time, their central black holes eventually sink toward the merged center due to dynamical friction. This process can take hundreds of millions of years, but it ultimately leads to the formation of a binary black hole system. As the two black holes orbit each other, they emit gravitational waves, gradually losing energy and spiraling closer until they merge into a single, more massive black hole. The resulting gravitational wave signal, like those detected by LIGO and Virgo, carries information about the masses, spins, and orientations of the merging pair. Such mergers are thought to be one of the main ways supermassive black holes grow over cosmic time. In some cases, the newly formed black hole receives a kick, a recoil velocity from the asymmetric emission of gravitational waves. These kicks can reach thousands of kilometers per second, fast enough to eject the black hole entirely from its host galaxy. Astronomers have found evidence of such wandering black holes, glowing faintly as they carry a small cluster of stars with them through intergalactic space. The interplay between black holes and galaxies is now a cornerstone of astrophysical research. Large-scale simulations like Illustris and Eagle have shown that including black hole feedback is essential for producing realistic galaxies. These models incorporate both radiative and kinetic feedback, allowing researchers to see how jets and winds redistribute energy and matter throughout a galaxy. The results align closely with observations from telescopes such as Chandra, ALMA, and the Hubble Space Telescope, confirming that black holes are integral to galaxy evolution. There's a delicate balance at work. Too much feedback, and the galaxy is stripped of gas, quenching star formation permanently. Too little, and the galaxy grows too quickly, violating observed scaling relationships. The M-sigma relation, the correlation between the mass of a galaxy's central black hole and the velocity dispersion of its stars, is evidence of this equilibrium. It shows that black hole growth and galactic structure are not independent, but tightly linked through billions of years of gravitational feedback. In essence, every galaxy is a partnership between stars, gas, dark matter, and one central gravitational anchor. Black holes may represent only a fraction of a percent of a galaxy's mass, but they control its fate. Through their outbursts and their quiet gravity alike, they sculpt the galaxies we see across the night sky. The effort to understand black holes has led physicists into one of the deepest challenges in science: reconciling general relativity and quantum mechanics. These two frameworks are the pillars of modern physics, yet they describe reality in fundamentally different ways. General relativity governs the large-scale structure of the universe, the motion of planets, stars, and galaxies through the curvature of space-time. Quantum mechanics, by contrast, rules the microscopic world of atoms and subatomic particles, where probabilities replace certainties and uncertainty is built into the fabric of reality. For most of physics, these two domains rarely overlap, but inside a black hole, and especially at its singularity, they collide head-on. The singularity predicted by general relativity is a region of infinite density and zero volume, a point where the known laws of physics break down. Yet infinities are usually a sign that the theory being applied is incomplete, not that nature itself is infinite. To truly understand what happens at a black hole's core, we need a theory of quantum gravity, one that unites Einstein's curved space-time with the probabilistic behavior of quantum mechanics. Hawking's discovery of black hole radiation was the first real glimpse of how these two realms might connect. By combining quantum field theory with curved space-time, Hawking showed that black holes aren't entirely black. They emit radiation. But his result also created a paradox. If black holes radiate and eventually evaporate, what happens to the information about the matter that fell into them? In quantum mechanics, information, the specific state of particles, cannot be destroyed. The wave function evolves deterministically, even if the outcomes appear random. But if a black hole evaporates completely, all that's left is thermal radiation, featureless and random, containing no trace of what went in. That seems to violate one of the most fundamental principles of physics: information conservation. This contradiction is known as the black hole information paradox. Physicists have debated it for decades, and it has become one of the defining puzzles in theoretical physics. Several possible resolutions have been proposed. One is that information is somehow encoded in the Hawking radiation itself, though in a way we don't yet understand. Another is that the information is preserved at the event horizon in a thin membrane or holographic layer. This idea, developed in part by Gerard T. Hooft and Leonard Susskind, led to the holographic principle, the notion that the information content of a volume of space can be represented entirely on its boundary surface. The holographic principle suggests that our universe might, in a sense, be like a projection, a three-dimensional reality emerging from two-dimensional information encoded at its edges. Though that sounds abstract, it has deep mathematical support in the ADS/CFT correspondence proposed by Juan Maldacena in 1997. In that framework, a gravitational system in a higher dimensional bulk space can be exactly equivalent to a quantum field theory without gravity on its lower dimensional boundary. It's one of the strongest hints yet that space-time and gravity might emerge from underlying quantum information. If true, the holographic view could resolve the information paradox. The information about what falls into a black hole would never truly be lost. It would be encoded on the event horizon and gradually released through Hawking radiation, Recent theoretical work supports this interpretation, suggesting that the total entropy and information balance can indeed be preserved. Still, other physicists argue for different mechanisms. Some propose that the event horizon is not as smooth as general relativity predicts, but instead a region filled with violent quantum fluctuations, a firewall that destroys information before it can cross. Others suggest that black holes might not evaporate completely, but leave behind stable remnants that retain the information indefinitely. None of these solutions has been confirmed experimentally, and each challenges core assumptions of either quantum mechanics or relativity. The search for quantum gravity has inspired multiple competing theories. String theory, for instance, posits that all particles are tiny vibrating strings existing in higher dimensional space. In this framework, gravity emerges naturally, and black holes can be modeled as specific string configurations whose entropy matches that predicted by Hawking's calculations. On the other hand, loop quantum gravity attempts to quantize space-time itself, describing it as a network of discrete loops rather than a continuous fabric. In that picture, the singularity inside a black hole might be replaced by a finite dense core, a Planck star, where quantum pressure prevents infinite collapse. Experimental tests of these ideas are challenging since black holes are distant and extreme, but new instruments are beginning to push the boundaries. The Event Horizon Telescope, which produced the first direct image of a black hole's shadow in 2019, is refining our understanding of how matter and light behave near the event horizon. Future observations could detect subtle deviations from classical predictions, clues to the quantum structure of spacetime. Gravitational wave observatories are another crucial tool. The ripples detected from black hole mergers carry information about the properties of the merged object. If quantum gravity effects exist, they might leave detectable imprints, tiny echoes following the main gravitational wave signal. Though no clear evidence has yet been found, the next generation of detectors could be sensitive enough to spot them. In particle physics, some speculative theories suggest that microscopic black holes might be produced in high-energy collisions, such as those in the Large Hadron Collider. If that were to happen, they would evaporate almost instantly through Hawking radiation, offering a direct test of the theory. So far, no such events have been observed, but experiments continue to probe the energy scales where gravity and quantum mechanics might begin to converge. The quest to understand black holes is therefore more than just an astrophysical pursuit. It's a search for the fundamental nature of reality. Every attempt to describe their behavior pushes physics closer to a unified framework, whether through holography, quantum geometry, or yet another unknown mechanism. Black holes remain the testing ground for our deepest theories. Observing a black hole directly is impossible. By definition, it emits no light. Yet modern astronomy has developed ways to detect and measure black holes through the effects they have on their surroundings. From the motion of stars to the bending of light and the flicker of X-rays, black holes reveal themselves not by what they show, but by what they do. The most obvious way to infer a black hole's presence is through gravity. When a massive but invisible object causes nearby stars or gas to move at extreme speeds, there's usually only one possible explanation. This is how the black hole at the center of our galaxy, Sagittarius A star, was confirmed. For more than 2 decades, astronomers tracked the orbits of stars near the Milky Way's core, using infrared telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile. These stars whipped around an unseen point at speeds up to 7,500 kilometers per second, about 4,600 miles per second. Their trajectories could only be explained by an object with 4 million times the mass of the Sun contained within a region smaller than our solar system. Similar methods have revealed black holes in other galaxies too, By analyzing the Doppler shifts in light from stars and gas clouds orbiting galactic centers, astronomers can calculate how fast they move and thus infer the central mass. The relationship between black hole mass and the velocity dispersion of stars, the m-sigma relation, has become one of the cornerstones of galactic astrophysics, showing that virtually every large galaxy hosts a central black hole. Beyond gravitational effects, black holes announce themselves through accretion, the process of pulling in gas and dust. As material spirals inward, it forms an accretion disk, flattened by angular momentum and heated by friction to millions of degrees. This disk emits intense radiation, especially in X-rays and ultraviolet light, which can outshine the entire host galaxy. Quasars, the brightest objects in the universe, are powered by such accretion processes onto supermassive black holes. X-ray observatories like Chandra, XMM Newton, and NU STAR have mapped this emission in detail. In some systems, the X-ray spectrum shows broad, skewed emission lines caused by the extreme gravitational field near the event horizon, a direct signature of Einstein's general relativity in action. These lines reveal how space and time are warped by the black hole's spin, letting astronomers measure the rotation rates of these otherwise invisible objects. Another phenomenon associated with black holes is the formation of relativistic jets, narrow streams of particles accelerated to nearly the speed of light and ejected along the black hole's poles. The mechanism behind these jets involves magnetic fields twisted by the rotation of the accretion disk and the black hole itself. The energy carried by jets can extend across thousands or even millions of light years, influencing galaxy evolution by heating and expelling surrounding gas. Radio telescopes are particularly well suited to observing jets. Arrays like the Very Large Array in New Mexico and the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, have captured images of these colossal outflows. In some cases, they form lobes of radio emission larger than the galaxy itself. These structures are not only visually striking, but also vital clues to how black holes release energy into their environment. The most dramatic breakthrough in direct black hole observation came in 2019, when the Event Horizon Telescope EEHT collaboration released the first image of a black hole's shadow, the supermassive black hole at the center of galaxy M87, about 55 million light-years away. The EHT is not a single telescope, but a network of radio observatories around the world, synchronized to act as one Earth-sized instrument through a technique called very long baseline interferometry. The resulting image showed a bright circular ring surrounding a dark core, the shadow of the event horizon. This shadow isn't the black hole itself, but the region where light from the surrounding accretion disk is bent and trapped by gravity. The size and shape of the ring matched predictions from general relativity almost perfectly. In 2022, the same technique was used to image Sagittarius A star, providing humanity's first direct view of the black hole at the heart of our own galaxy. Observations like these have turned black holes from theoretical curiosities into empirical science. By measuring the shape of the shadow, astronomers can test general relativity under conditions that can't be recreated anywhere else. Even tiny deviations could signal new physics, perhaps clues to quantum gravity or alternative models of space-time. Another powerful tool for studying black holes is gravitational lensing, the bending of light around a massive object. When a black hole passes between a distant light source and an observer, it distorts and magnifies the background light, creating multiple images, arcs, or rings. These effects have been observed with galaxies and clusters acting as lenses, and though individual black holes are harder to catch in this configuration, microlensing surveys sometimes reveal compact objects, possibly isolated black holes drifting through space. Even when no light is visible, gravitational waves have opened a new window on black hole physics. Since 2015, detectors like LIGO and Virgo have recorded dozens of black hole mergers, each producing a unique chirp as the two objects spiral together and collide. These events confirm the existence of binary black holes and provide precise measurements of their masses and spins. Some of the detected mergers involve surprisingly large black holes, hinting at new pathways of formation. Each method, stellar motion, accretion emission, jets, lensing, and gravitational waves, provides a different piece of the puzzle. Together, they paint a coherent picture of black holes as active, measurable components of the universe rather than abstract singularities. What once existed only in mathematical equations is now observed across the electromagnetic spectrum and through the very fabric of space-time itself. Black holes come in a wide range of sizes, and though the basic physics governing them is the same, their origins and effects differ dramatically across scales. Astrophysicists generally classify them into four main categories: stellar mass, intermediate mass, supermassive, and primordial black holes. Each represents a different stage in the cosmic hierarchy and offers a unique glimpse into how gravity sculpts matter and energy across the universe. Stellar mass black holes are the most common and best understood. They form when massive stars, generally more than about 20 to 30 times the mass of the Sun, exhaust their nuclear fuel and undergo core collapse. In such stars, fusion no longer provides enough outward pressure to counter gravity, and the core implodes. If the remnant mass exceeds roughly 3 solar masses, not even neutron degeneracy pressure can stop the collapse, and a black hole is born. These black holes typically range from about 3 to a few dozen times the mass of the Sun. They are scattered throughout galaxies, often found in binary systems where one normal star orbits a black hole companion. In these systems, the black hole can pull material from the companion star, forming an accretion disk that emits strong X-rays. This makes them detectable even though the black hole itself remains invisible. Famous examples include Cygnus X1, one of the first confirmed stellar black holes, located about 6,000 light-years from Earth. Its companion star orbits a dark object roughly 15 times the Sun's mass, and the X-ray radiation from the system matches the behavior predicted for an accreting black hole. Many other systems like it have been identified, allowing scientists to study black hole masses, spins, and accretion behavior in detail. Intermediate mass black holes occupy the gap between stellar mass and supermassive black holes, roughly 100 to a few 100,000 solar masses. For decades, they were hypothetical, as few clear observational signatures existed. But evidence is growing. Some ultra-luminous X-ray sources and compact star clusters show signs of containing black holes in this mass range. The formation of intermediate black holes remains an open question. One possibility is that they are the products of repeated mergers of stellar mass black holes inside dense star clusters. Another idea is that they formed early in the universe, as remnants of massive primordial stars or through direct collapse of gas clouds. These objects could be the missing link between ordinary stellar black holes and the giant ones found at galactic centers. In 2020, the LIGO and Virgo detectors observed a merger between two black holes of 66 and 85 solar masses, producing a final black hole of about 142 solar masses. This was the first direct detection of an intermediate mass black hole. Its existence helps fill a long-standing gap in the population and supports the idea that such objects form through hierarchical merging. Supermassive black holes are the cosmic heavyweights, with masses ranging from millions to tens of billions of suns. They sit at the centers of galaxies, including our own Milky Way, and act as engines for active galactic nuclei and quasars. Their formation remains one of the biggest unsolved mysteries in astrophysics. As discussed earlier, they may have grown from smaller seeds, either stellar remnants or direct collapse black holes that accreted gas and merged over cosmic time. Despite their enormous mass, Supermassive black holes are relatively gentle near their event horizons because tidal forces scale inversely with size. If you fell toward one of these giants, you could theoretically cross the event horizon without being torn apart immediately, unlike in the case of a smaller black hole, where tidal forces would rip you apart, a process grimly known as spaghettification. Supermassive black holes are central to galactic dynamics. Their gravitational influence extends far beyond the accretion disk, shaping the motion of stars and gas throughout the bulge. The energy they release through jets and radiation regulates star formation and can even blow gas out of the galaxy entirely, determining its future evolution. At the extreme end of this category lies TON 618, one of the most massive black holes ever measured, with an estimated mass of around 66 billion suns. Its accretion disk shines with more than 100 trillion times the luminosity of the sun, visible from over 10 billion light-years away. Objects like TON 618 remind astronomers how early and efficiently black holes must have formed in the universe's history. Primordial black holes, the most speculative category, would have formed not from stars, but from density fluctuations in the first fractions of a second after the Big Bang. During this brief period, regions of the universe could have been dense enough to collapse under their own. Gravity, producing black holes with masses ranging from microscopic scales to thousands of suns. No primordial black hole has yet been confirmed, but their existence could explain several mysteries. If small primordial black holes formed in large numbers, they might account for some or all of the dark matter, the invisible mass that makes up most of the universe's gravitational content. Smaller ones with masses less than about 10 to the power of 12.12 kilograms, roughly the mass of a large mountain, would have evaporated by now through Hawking radiation, possibly leaving observable traces in the form of high-energy gamma rays. Detecting primordial black holes is challenging. Astronomers search for them through gravitational microlensing events, where a compact object briefly magnifies the light from a distant star. So far, surveys like OGLE and MACHO have placed limits on how many primordial black holes could exist in certain mass ranges. Upcoming observatories, such as the Vera Rubin Observatory and future gravitational wave detectors, may provide more decisive evidence one way or another. Together, these four types of black holes form a kind of cosmic ecosystem. The small ones are born in stellar deaths, the medium ones bridge the evolutionary gap, the giant ones power galaxies, and the hypothetical primordial ones may connect cosmology to particle physics. Despite their differences, all share one defining feature: an event horizon, the point beyond which the known laws of physics cease to operate in any conventional sense. At the heart of every black hole lies its defining feature: the event horizon. This is the ultimate boundary in the universe, a one-way surface where escape becomes impossible. Nothing, not even light, can climb back out once it crosses that invisible threshold. The event horizon isn't a physical surface like the crust of a planet. It's a region of space-time so warped by gravity that all possible paths forward lead inward, toward the singularity. To understand how it forms, it helps to recall the concept of escape velocity, the speed required to break free from an object's gravitational pull. For Earth, the escape velocity is about 11.2 kilometers per second, roughly 25,000 miles per hour. For the Sun, it's around 617 kilometers per second, about 384 miles per second. As mass becomes more concentrated, gravity intensifies, and the escape velocity increases. If enough mass is squeezed into a small enough volume, the escape velocity exceeds the speed of light, about 300,000 kilometers per second, or 186,000 miles per second. At that point, light itself can't escape, and the object becomes a black hole. For a non-rotating, uncharged black hole, described by the Schwarzschild solution to Einstein's equations, the event horizon's radius, known as the Schwarzschild radius, is given by the formula RS equals 2 GMC squared RS equals 2 GMC squared, where GGG is the gravitational constant, MMM is the mass, and CCC is the speed of light. For a black hole with the mass of the Sun, this radius is about 3 kilometers, roughly 1.9 miles. For a black hole 10 times as massive, it's about 30 kilometers, 19 miles. Supermassive black holes can have horizons millions of kilometers wide, larger than the orbit of Mercury. To an outside observer, the event horizon behaves strangely. Anything falling toward it appears to slow down as it approaches, due to gravitational time dilation. From our perspective, time near the horizon seems to almost stop, and the object appears frozen just above it, fading slowly as its light is redshifted into invisibility. Yet from the falling object's own perspective, it crosses the event horizon without noticing anything special. At least according to classical physics. Inside, all possible directions lead further inward, and the singularity lies in its future, the way tomorrow lies in ours. The warping of space-time near the horizon also distorts how light travels. Photons emitted from just outside the horizon are bent by gravity, creating the glowing ring seen in images from the Event Horizon Telescope. This ring is about 2.6 times larger than the actual event horizon, an effect of gravitational lensing. In this way, even though the horizon itself can't be seen, its shadow can, a silhouette carved out of space-time by gravity. In rotating black holes described by the Kerr solution, the structure becomes even more complex. Rotation drags space-time around with it, a phenomenon called frame dragging. Near the rotating black hole, space itself is pulled into motion, meaning that any object, even one trying to remain stationary, is forced to move around the black hole. The region where this occurs is called the ergosphere, lying just outside the event horizon. Inside the ergosphere, it's possible for an object to escape by taking advantage of the black hole's spin. This process, known as the Penrose process, allows energy to be extracted from a rotating black hole by splitting a particle pair near the ergosphere, one falling in, the other escaping with more energy than the original. In principle, this could serve as an incredibly efficient energy source, though in practice, it's purely theoretical. The same principle, however, may power the colossal jets seen in active galaxies, where magnetic fields extract rotational energy from the black hole and channel it outward. Another counterintuitive feature near the event horizon is gravitational time dilation. According to general relativity, time flows more slowly in stronger gravitational fields. For an observer hovering near the event horizon, seconds would pass far more slowly than for someone far away. In extreme cases, billions of years could pass in the universe outside, while only minutes pass for someone near the horizon. This effect has been confirmed experimentally in weaker gravitational fields, such as near Earth and in orbit, and it becomes extreme near black holes. Once an object crosses the horizon, its fate is sealed. Classical physics predicts that it will continue falling until it reaches the singularity, a point of infinite density where the known laws of physics break down. But this singularity may not truly be a point. It's likely a sign that our equations are incomplete, and that quantum gravity would reveal a more realistic description of what happens at such extreme densities. From an information standpoint, the event horizon acts as a kind of cosmic sensor. It hides whatever happens inside from the rest of the universe, preserving the rule that no information can travel faster than light. Yet paradoxically, the horizon may also encode all the information about what falls in, as suggested by the holographic principle. To an outside observer, the horizon becomes the repository of everything that's been lost to view, a cosmic memory surface where physics and information theory intersect. Despite being invisible, the event horizon defines everything about a black hole's behavior. Its size determines the black hole's entropy, its shape depends on rotation, and its interactions with light shape the images we see. In a sense, the event horizon is the black hole, not a thing in space, but a boundary between the known and the unknowable, where geometry becomes destiny and time itself is drawn to an end. When matter approaches a black hole, it enters one of the most violent and extreme environments in the universe. Gravity, radiation, and motion all reach extraordinary intensities, turning what might begin as ordinary gas or dust into a luminous, chaotic storm of plasma spiraling toward oblivion. Understanding this process, what happens to matter as it nears and crosses the event horizon, has been central to modern astrophysics, both for what it reveals about black holes and for what it teaches us about the limits of physical law. Most matter doesn't fall straight into a black hole. Instead, because of angular momentum, it forms an accretion disk, a rotating, flattened structure that behaves like a cosmic whirlpool. As particles in the disk orbit closer to the center, friction and turbulence between them convert gravitational energy into heat. This heating raises the temperature of the disk to millions of degrees, causing it to emit radiation across the spectrum, from visible light to X-rays. In fact, accretion disks are among the brightest continuous sources in the universe. They are the engines that power quasars and active galactic nuclei. The dynamics of accretion are governed by complex magnetohydrodynamics, the interplay of magnetic fields and fluid motion. Magnetic fields thread through the disk, twisting and reconnecting in violent bursts that transport angular momentum outward and allow matter to move inward. Without this transfer of angular momentum, material would remain in stable orbits indefinitely, unable to fall into the black hole. In this way, magnetic turbulence effectively acts as a form of viscosity, enabling the inward drift of matter and the outward flow of energy. As material spirals closer, relativistic effects dominate. Time slows, space stretches, and orbits become unstable near the innermost stable circular orbit, ISCO. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. Inside that, no stable circular paths exist. Any disturbance sends matter plunging toward the event horizon in a final rapid descent. The energy released by accretion is immense. For comparison, nuclear fusion, the process that powers stars, converts about 0.7% of the mass of hydrogen into energy. Accretion onto a black hole can convert up to 40% of the infalling mass into radiation, depending on the spin of the black hole. This efficiency makes accretion the most powerful energy conversion. Process known, explaining why quasars can outshine entire galaxies despite being only light days across. As matter falls inward, it emits radiation that we can detect. In stellar mass black holes, this radiation often varies rapidly, flickering on timescales of milliseconds, corresponding to orbital periods near the ISCO. These variations provide clues about the size, spin, and accretion rate of the black hole. For supermassive black holes, the timescales are much longer, sometimes days or weeks, but the same physics applies. Eventually, as material crosses the event horizon, all outward signals cease. To a distant observer, the infalling matter appears to slow down and fade due to gravitational redshift. Its light stretch to longer and longer wavelengths until it disappears completely. But from the falling object's own perspective, time proceeds normally, and the horizon is crossed without fanfare. Inside, all paths lead inward, and escape is impossible. As it continues toward the singularity, the object experiences tidal forces, differences in gravitational pull between its near and far sides. These forces stretch the object along the direction of the gravitational gradient and compress it along perpendicular directions. Near smaller black holes, where the curvature of space-time is extreme, these tidal forces can be catastrophic. The object would be torn apart atom by atom in a process aptly nicknamed spaghettification. For example, near a 10 solar mass black hole, the tidal forces strong enough to destroy a human body occur well outside the event horizon. But for a supermassive black hole, the situation is different. Because the gravitational gradient near the horizon is weaker for larger masses, a person could theoretically cross the event horizon of a billion solar mass black hole without feeling significant tidal effects, though survival beyond that point would still be impossible in the long run. Spaghettification has been indirectly observed on cosmic scales in what astronomers call tidal disruption events, TDES. These occur when a star passes too close to a black hole and is torn apart by tidal forces. Part of the stellar material is ejected into space, while the rest falls inward, producing a sudden flare of radiation. In recent years, observatories like Swift and the Zwicky Transient Facility have captured several such events in progress. They provide a rare glimpse of a black hole in the act of consuming a star. The energy released in a TDEE can rival that of a supernova. The flare often brightens over weeks, peaks in ultraviolet or X-rays, and then fades as the debris either escapes or settles into an accretion disk. These events also help measure black hole masses, since the timing and luminosity of the flare depend on the size of the black hole and the nature of the disrupted star. As matter falls in, not all of it is lost. Some is redirected by magnetic fields into relativistic jets, narrow streams of plasma that shoot out from the poles of the black hole at nearly the speed of light. The exact mechanism behind jet formation is still under study, but it likely involves twisted magnetic field lines anchored in the accretion disk and the black hole's rotation. These jets can extend for thousands or even millions of light years, transporting enormous amounts of energy far from the black hole's immediate vicinity. In the case of supermassive black holes, such jets are visible across the electromagnetic spectrum, from radio to gamma rays, and can shape entire galaxies by heating or expelling gas. On smaller scales, similar jets appear in microquasars, stellar mass black holes within our galaxy. Their rapid, repeating outbursts allow astronomers to study black hole feeding and feedback in real time, on human timescales. Ultimately, everything that falls toward a black hole participates in a process that blends gravity, motion, and energy into one of nature's most extreme displays. Whether it's a star, a cloud of gas, or a lone particle, each follows the same fate, accelerated, heated, and stretched by gravity until it vanishes from view. To the outside universe, it's gone forever. To physics, it's part of the ongoing experiment at the edge of what can be known. Once matter passes the event horizon, it enters a region where classical physics loses all predictive power. The interior of a black hole, as described by general relativity, leads inevitably toward a singularity, a point of infinite density and zero volume where space-time curvature becomes infinite. But infinity in physics usually signals a breakdown, not an actual physical quantity. It means the equations we use are being pushed beyond their domain of validity. In this case, it tells us that relativity alone cannot describe what truly happens inside a black hole. According to Einstein's field equations, once inside the event horizon, every possible path through space-time, every potential future, leads inward. There is no way to remain stationary, no way to orbit, and no way to turn around. Space and time effectively trade roles. What we think of as moving forward in time outside the horizon becomes equivalent to moving toward the singularity inside it. For any object or signal, the singularity lies as inevitably ahead as tomorrow. If general relativity were the whole story, the singularity would represent the ultimate endpoint of matter and information. All structure would be crushed into an infinitely small region. Density, temperature, and curvature would diverge to infinity, and all meaningful distinctions between objects would vanish. This scenario is known as the cosmic censorship hypothesis, proposed by Roger Penrose, which states that singularities are always hidden behind event horizons. Naked singularities cannot exist in nature. This principle maintains cosmic order by keeping the breakdown of physics safely out of view. However, most physicists believe that singularities are artifacts of an incomplete theory. Quantum mechanics must come into play at such extreme densities, and the union of quantum theory with general relativity, the long-sought theory of quantum gravity, would likely smooth out the infinities. Several leading candidates, such as string theory and loop quantum gravity, propose mechanisms that could resolve the singularity into something finite and physically meaningful. In string theory, all fundamental particles are tiny vibrating strings, not point-like objects. At the scale of the Planck length, about 1.6 times 10 to the negative 351.6 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 times n to the negative 351.6 times 10 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 to the negative 10 to the power of negative 35 1.6 times 10 to the power of negative 35 meters, roughly 10 to the negative 35 yards, unimaginably small. Space-time may not be continuous, but rather quantized, with a minimum possible length. This would prevent the formation of an actual point singularity, replacing it with a finite region of extremely dense but structured spacetime. Loop quantum gravity takes a different approach, suggesting that space itself is made of discrete loops of quantum fields. In this model, the interior of a black hole could undergo a kind of bounce, where collapsing matter reaches a maximum finite density and then re-expands, possibly giving rise to a new region of spacetime. This leads to speculative ideas that black holes might connect to other universes or spawn new ones, although such hypotheses remain beyond observational reach. Another intriguing idea involves quantum tunneling. If the classical singularity is replaced by a finite quantum state, there may be a small but non-zero probability that information or matter could tunnel out again, perhaps in a drastically transformed form. Some physicists propose that black holes could eventually release their contents, albeit after incredibly long timescales, through quantum processes related to Hawking radiation. Inside the event horizon, the concept of space and time becomes deeply distorted. Coordinates that describe distance outside the horizon no longer have the same meaning. Instead of space being radial and time being linear, they swap roles. The radial direction becomes time-like, and time itself becomes spatial. This inversion makes it impossible to stop moving inward, because doing so would be equivalent to trying to stop time. For rotating black holes, the internal structure is even stranger. The Kerr solution predicts not a single point singularity, but a ring singularity, a rotating loop of infinite density surrounded by a region where causality breaks down. The equations even allow for the existence of a white hole region, or a passage to another universe, often called a wormhole. In theory, a traveler falling into a rotating black hole could pass through the ring singularity and emerge elsewhere. But in practice, such paths would likely be unstable. Any slight disturbance would collapse the wormhole before it could be traversed, destroying the traveler in the process. No one knows what truly lies inside a black hole. We can model the outer regions with extraordinary precision, as proven by gravitational wave detections and the Event Horizon Telescope images, but the interior remains a domain of speculation. It represents the limit of human physics, where our best theories contradict each other. Relativity insists on a smooth space-time fabric that curves infinitely under extreme gravity. Quantum mechanics, on the other hand, refuses to allow infinities, demanding discrete energy levels and uncertainty. The resolution of this conflict may come only with a complete theory of quantum gravity. Such a theory would not only describe black holes' interiors, but also explain the very origin of space and time. In that sense, black holes aren't just cosmic oddities. They are natural laboratories for testing the most fundamental principles of reality. Despite the mystery, one thing remains clear. What happens beyond the event horizon is not lost to the universe entirely. It influences the outside through gravity, rotation, and the radiation emitted before the horizon is crossed. The boundary between inside and outside might be absolute from a local perspective, but its effects ripple outward in measurable ways, hinting that the universe may keep a more careful record than we currently understand. In the 1970s, physicist Stephen Hawking made a discovery that forever changed how we think about black holes. Until then, they were believed to be perfectly one-way objects. Matter and energy could fall in, but nothing could ever come out. Hawking, combining principles from quantum mechanics and general relativity, showed that this wasn't entirely true. Under certain conditions, black holes can emit radiation, a faint thermal glow, now known as Hawking radiation. To understand this phenomenon, we need to look at how quantum physics describes empty space. What we call vacuum isn't truly empty. It's filled with continuous fluctuations, where pairs of virtual particles and antiparticles constantly pop in and out of existence. Normally, these pairs annihilate almost immediately, returning their borrowed energy to the vacuum. But near the event horizon of a black hole, the situation changes. When one of these virtual pairs forms near the horizon, gravity can separate them. One particle may fall into the black hole while the other escapes into space. To an outside observer, it appears as if the black hole has emitted a real particle. Energy conservation requires that the particle falling inward have negative energy relative to the outside universe, effectively reducing the black hole's total mass. Over immense timescales, this process causes the black hole to slowly evaporate. The temperature of this radiation depends inversely on the black hole's mass. A stellar mass black hole with several times the mass of the Sun, has a temperature of only about 10 to the minus 80 Kelvin, far colder than the cosmic microwave background radiation that fills the universe. This means such black holes absorb more radiation than they emit and therefore gain mass overall. Only very small black holes, much smaller than a mountain, would emit measurable Hawking radiation today. If Hawking's theory is correct, then black holes are not eternal. Over unimaginably long periods, they lose mass, shrink, and eventually vanish in a final burst of radiation. For a solar mass black hole, the timescale for complete evaporation is on the order of 10 to the power of 67, a number so vast it dwarfs the current age of the universe, which is about 1.38 times 10 to the power of 110 to the power of 10 1.38 times 10 to the power of 10 years. For supermassive black holes, the evaporation time is even longer, effectively infinite on any human or galactic scale. This discovery led to one of the most important and perplexing questions in modern physics, the black hole information paradox. According to quantum mechanics, information can never be destroyed, even if a system changes form, burning to ash, dissolving in acid, or collapsing into a star. The total information about its initial state is preserved, encoded in the resulting particles. But Hawking radiation appears purely thermal, containing no trace of the information about what fell into the black hole. If a black hole eventually evaporates completely and the radiation carries no information, that information would be lost forever, a direct violation of quantum mechanics. This contradiction sparked decades of debate between physicists, and it remains one of the deepest unresolved problems in theoretical physics. Various solutions have been proposed. One idea is that the information is somehow encoded in subtle correlations within the Hawking radiation itself, though too complex to detect directly. Another is that it's stored on the event horizon in a kind of holographic form, a concept related to the holographic principle proposed by Gerard T. Hooft and Leonard Susskind. This principle suggests that all the information within a volume of space can be represented on its two-dimensional boundary. Applied to black holes, it implies that the surface area of the event horizon, not the volume inside, measures the black hole's entropy, the total information it contains. In simple terms, the entropy of a black hole measures the number of microscopic configurations that could give rise to the same macroscopic appearance. A larger event horizon means more possible states, and thus higher entropy. This also means that when two black holes merge, the total horizon area, and therefore the entropy, always increases, just as the second law of thermodynamics demands. The idea that the universe might fundamentally be holographic, that the three-dimensional world we perceive could be a projection of information encoded on a distant two-dimensional surface, has far-reaching implications. It provides a potential bridge between general relativity and quantum mechanics, and has inspired entire research fields, such as the ADS/CFT correspondence in string theory. Despite all these advances, the information paradox is not fully resolved. Some researchers argue that black holes never completely evaporate, leaving behind a stable remnant that stores the information. Others suggest that the information escapes gradually, encoded in correlations between emitted particles, a process known as black hole unitarity restoration. A more radical idea, known as the firewall hypothesis, proposes that the event horizon is not smooth, but a searing boundary wherein falling matter is destroyed, breaking the equivalence principle of relativity. Each of these possibilities challenges some aspect of known physics. The debate continues because no experiment can yet probe these extreme conditions directly. Nonetheless, the study of Hawking radiation and black hole thermodynamics has already reshaped our understanding of the universe. It showed that black holes are not just gravitational traps, but thermodynamic systems, objects with temperature, entropy, and energy exchange. In doing so, it revealed that the laws governing the cosmos are deeply interconnected. Gravity, quantum theory, and thermodynamics, three domains once thought separate, meet at the edge of a black hole's event horizon. The fact that we can even discuss the temperature of something from which light cannot escape is a reminder that the universe, while consistent, rarely behaves as intuition expects. Over cosmic timescales, black holes evolve just like everything else in the universe, slowly, quietly, and with consequences that stretch across billions or even trillions of years. Though they may seem like permanent fixtures, they too have a life cycle governed by gravity, energy exchange, and the expansion of the cosmos itself. Understanding their long-term evolution gives us a window not just into astrophysics, but into the future history of the universe. A black hole's development begins with its formation. Stellar mass black holes form when massive stars, usually more than about 3 times the mass of the Sun, exhaust their nuclear fuel. Without the outward pressure generated by fusion, the star's core collapses under gravity. If the mass is sufficient, even neutron degeneracy pressure, which supports neutron stars, cannot resist the collapse. The core then implodes, forming a black hole in a fraction of a second. The outer layers may be expelled in a supernova or fall back in, feeding the new black hole. Once formed, a black hole can grow through 2 main processes: accretion and mergers. Accretion occurs when nearby gas, dust, or stars fall inward, releasing gravitational energy as they spiral in. This process is often seen in binary systems, where a black hole pulls matter from a companion star. Mergers, on the other hand, occur when 2 black holes collide, combining their masses and releasing enormous bursts of energy in the form of gravitational waves. These waves, ripples in space-time predicted by Einstein and first observed in 2015 by the LIGO collaboration, have become one of the key tools for studying black hole evolution. Each merger slightly distorts the structure of space-time, producing a characteristic chirp in gravitational wave detectors. The frequency and amplitude of the signal reveal the masses and spins of the merging black holes, as well as the distance to the event. From these observations, astronomers have begun to piece together the demographics of black holes in the universe, their typical masses, how often they collide, and how they may build up into larger systems. At galactic centers, black holes reach scales far beyond stellar origins. Supermassive black holes with millions to billions of solar masses reside in nearly every large galaxy. Their formation remains one of the great puzzles of cosmology. It's possible they grew from smaller seed black holes formed in the early universe, or from the direct collapse of massive gas clouds shortly after the first stars ignited. Either way, they must have grown quickly, since quasars powered by billion solar mass black holes already existed less than 1 billion years after the Big Bang. Over time, galaxies merge, and with them their central black holes. When this happens, the 2 black holes spiral inward, losing energy through gravitational radiation until they coalesce. The resulting single black hole carries away a recoil kick that can reach thousands of kilometers per second, or several thousand miles per second. In extreme cases, the merged black hole could be ejected entirely from its host galaxy, drifting through intergalactic space. As the universe ages, the supply of available matter decreases, star formation slows, gas clouds are consumed or expelled, and black holes become increasingly isolated. Without accretion or mergers, they enter long periods of dormancy, emitting virtually no radiation except the faint Hawking radiation predicted by quantum theory. Over unimaginably long timescales, far longer than the current age of the universe, Hawking radiation becomes the dominant process. Small black holes evaporate faster than large ones because their temperature is inversely proportional to mass. A black hole with the mass of a mountain, for instance, would evaporate in about 10 to the power of 10 years, roughly the current age of the universe, while one with the mass of the Sun would take around 106,710 to the power of 167 years. A supermassive black hole containing billions of solar masses would require on the order of 10 to the power of 100 years or more to fully evaporate. In the distant future, when stars have burned out and galaxies have faded, black holes will be the last major structures remaining. This era, sometimes called the black hole era, represents the final chapter of cosmic evolution. During it, occasional mergers may still occur, but energy emission will be rare. Eventually, Hawking radiation will cause all black holes, regardless of size, to shrink. The smallest ones will vanish first in bursts of high-energy radiation, while the largest will linger for eons. The final moments of a black hole's life are thought to be violent on a microscopic scale. As the black hole's mass decreases, its temperature rises, and the rate of radiation increases. Near the end, it emits intense gamma rays and particles, potentially releasing its remaining energy in a final explosive flash. However, this is still a theoretical picture. No such event has ever been observed, and the physics of the final evaporation phase likely requires a complete quantum gravity description. When the last black hole evaporates, the universe will be almost completely dark. Only a thin, diffuse sea of low-energy photons, neutrinos, and elementary particles will remain, slowly spreading through an ever-expanding void. This vision of the cosmos, vast, cold, and nearly featureless, is known as the heat death of the universe. It's the natural consequence of the second law of thermodynamics. As entropy increases, energy becomes evenly distributed, leaving no gradients to drive processes like star formation, radiation, or life. There is one speculative loophole to this ultimate fate. If quantum effects allow black holes to leave behind stable remnants after evaporation, then these remnants might persist indefinitely, storing the final traces of information from everything that once existed. Whether this happens depends on details of quantum gravity that remain unknown. Even so, black holes represent not just destruction, but transformation. They recycle matter into energy, seed galaxy formation, and shape the large-scale structure of the cosmos. From stellar collapse to cosmic extinction, they bookend the history of the universe. If anything endures beyond the current epoch of stars, it will likely be their gravitational shadows, silent, invisible, and ancient beyond comprehension. Despite their name, black holes are not entirely invisible. While no light can escape from within the event horizon, the regions around them often blaze with radiation, motion, and gravitational effects strong enough to be observed across vast distances. Over the last century, astronomers have developed a range of techniques to detect black holes indirectly, to measure their masses, and to study their environments in detail. What was once purely a theoretical construct has now become a well-established and observable part of the cosmos. The first hints of black holes came from binary star systems, pairs of stars orbiting each other under mutual gravity. In some of these systems, only one member was visible, yet the visible star's motion suggested it was orbiting an unseen, extremely massive companion. If the mass of that invisible partner exceeded about 3 solar masses and produced no detectable light, the simplest explanation was a black hole. One of the earliest and most famous examples is Cygnus X1, located about 6,000 light-years away. Detected in the 1960s as a strong source of X-rays, it was later found to be part of a binary system where a bright blue supergiant star orbits an unseen companion roughly 15 times the mass of the Sun. The X-rays are produced as gas from the visible stars pulled toward the compact object, forming an accretion disk heated to millions of degrees. Observations over decades have confirmed that the hidden object fits all known properties of a stellar mass black hole. X-ray binaries like Cygnus X1 remain a primary way to study black holes in our galaxy. The behavior of the emitted radiation, its intensity, spectrum, and variability, reveals details about accretion processes and relativistic effects near the event horizon. Rapid fluctuations in brightness occurring on millisecond timescales indicate that the radiation originates from regions only a few tens of kilometers, a few dozen miles, across, consistent with the size of a stellar black hole. At much larger scales, supermassive black holes make their presence known through the activity of galactic cores. Active galactic nuclei, AGN, and quasars are powered by enormous black holes accreting matter at high rates. The energy released by accretion can outshine entire galaxies, producing intense radiation and relativistic jets that extend for thousands or even millions of light years, or roughly the same number of miles. These luminous beacons allow astronomers to detect black holes at distances corresponding to when the universe was less than 1 billion years old. Another key observational breakthrough came with the study of stellar motions near the centers of galaxies. In the 1990s, using advanced infrared telescopes, astronomers tracked the orbits of individual stars around the core of the Milky Way. They found several stars moving at thousands of kilometers per second, following elliptical paths around an invisible point. The only plausible explanation was a compact object about 4 million times the mass of the Sun, now known as Sagittarius A*, the supermassive black hole at the heart of our galaxy. This discovery provided direct evidence for the existence of supermassive black holes, and similar techniques have since revealed such objects in many other galaxies. The motion of stars and gas near the centers of galaxies consistently shows that enormous masses are concentrated in regions smaller than our solar system, leaving no alternative but a black hole. In 2015, a new form of observation revolutionized the field: gravitational wave astronomy. The Laser Interferometer, Gravitational Wave Observatory, LIGO, detected ripples in spacetime produced by the merger of two black holes about 1.3 billion light-years away. The signal, lasting only a fraction of a second, matched the predictions of general relativity almost perfectly. For the first time, astronomers had directly observed a black hole collision, not through light, but through gravity itself. Since then, dozens of additional detections have followed, involving black holes of various masses and spins. These observations have opened a new window on the universe, allowing scientists to test relativity in the strongest possible fields. Gravitational wave signals also reveal how frequently such mergers occur, how black holes form, and how they evolve across cosmic history. In 2019, another milestone was achieved with the release of the first direct image of a black hole's shadow. The Event Horizon Telescope, EHT, a global network of synchronized radio telescopes spanning the Earth, captured the silhouette of the supermassive black hole at the center of the galaxy M87, located 55 million light-years away. The image showed a bright circular ring surrounding a dark central region, consistent with the theoretical prediction of light bending around a black hole's event horizon. This observation was a triumph of both technology and theory. The ring's size and shape confirmed the presence of a black hole about 6.5 billion solar masses, and the pattern of brightness matched simulations based on Einstein's equations. In 2022, the EHT team achieved the same feat for Sagittarius A*, producing the first image of the black hole at the center of our own galaxy. Despite being 1,000 times smaller and far more variable, it displayed the same fundamental structure, confirming that the same physical principles apply from small to enormous scales. Each of these methods, X-ray observations, stellar motion tracking, gravitational waves, and direct imaging, probes a different aspect of black hole behavior. Together, they form a coherent picture. Black holes exist. They interact dynamically with their surroundings, and their properties match the predictions of general relativity to a remarkable degree. Future observatories promise to push this understanding even further. Projects like the Laser Interferometer Space Antenna, LISA, will detect lower-frequency gravitational waves from supermassive black hole mergers, while next-generation X-ray telescopes will resolve finer details of accretion disks and jets. Advances in radio interferometry will sharpen our view of event horizons themselves, potentially revealing time-variable structures in real time. The fact that we can now observe black holes, objects defined by their invisibility, is one of the most striking achievements of modern science. It demonstrates not only the power of theory and technology, but also the predictive strength of physics itself. What began as an abstract. Mathematical curiosity has become one of the most empirically confirmed phenomena in the cosmos. When matter or light approaches a black hole, the effects of Einstein's general theory of relativity become dominant. Gravity is no longer a simple force pulling objects together. It becomes a curvature of space-time so strong that space and time themselves behave differently than they do anywhere else in the universe. This leads to phenomena such as gravitational time dilation, redshift, and light bending, which can all be observed to varying degrees around massive objects. Near a black hole, these effects reach their extreme limits, testing relativity under conditions that no laboratory on Earth could replicate. Time dilation near a black hole is perhaps the most counterintuitive of these effects. According to general relativity, gravity slows the passage of time relative to regions farther away. This means that a clock positioned close to a massive body ticks more slowly than one located far from it. The greater the gravitational field, the more pronounced the difference. Near a black hole, where space-time curvature is extreme, this difference becomes enormous. To visualize this, imagine an astronaut orbiting near the event horizon of a black hole, while a second astronaut remains at a safe distance. The one near the black hole would experience time at a much slower rate. Minutes for the orbiting astronaut could correspond to years, centuries, or even millennia for the distant observer. To the person falling in, nothing unusual would appear to happen. Time would seem normal, but to everyone else, their movements would appear to slow down and eventually freeze as they approach the event horizon. This effect is a direct consequence of how space-time warps under intense gravity. The closer one gets to the horizon, the stronger the redshift. Light emitted from near the horizon is stretched to longer wavelengths as it climbs out of the gravitational well. A bright flash of light emitted just outside the event horizon would appear increasingly redder and fainter to a distant observer, eventually fading into darkness. This is why infalling matter appears to freeze and dim as it nears the horizon, even though it continues inward in its own frame of reference. Gravitational redshift has been confirmed experimentally, though of course not at black hole intensities. In 1959, the Pound-Rebka experiment at Harvard University measured the shift in gamma rays moving up and down a vertical height of only 22.5 meters, about 74 feet. Even over such a small distance, the experiment verified the gravitational redshift predicted by Einstein with extraordinary precision. Later, atomic clock experiments aboard satellites confirmed that time runs faster in weaker gravitational fields, forming the foundation for systems like GPS, which must correct for both special and general relativistic effects to maintain accuracy. At much larger scales, observations of light from stars near the center of our galaxy have provided indirect confirmation of these relativistic effects near a supermassive black hole. In 2018, astronomers using the European Southern Observatory's Very Large Telescope observed the star S2 as it passed within 120 astronomical units, about 11 billion miles or 18 billion kilometers, of Sagittarius, a star. the light from S2 showed a gravitational redshift exactly as predicted by general relativity, the first direct observation of such an effect in the field of a supermassive black hole. Light bending, another hallmark of relativity, occurs because massive objects curve spacetime, and light follows that curvature. Near a black hole, the bending is so extreme that light can orbit it entirely, forming what is known as the photon sphere. For a non-rotating black hole, this occurs at 1.5 times the Schwarzschild radius. Inside that radius, light cannot maintain a stable orbit and inevitably falls inward. The bending of light by gravity, known as gravitational lensing, was one of the first experimental confirmations of general relativity. In 1919, during a solar eclipse, astronomers led by Arthur Eddington measured the apparent shift in position of stars near the sun's edge. The observed deflection matched Einstein's predictions precisely, proving that light is affected by gravity. Today, gravitational lensing is used on cosmic scales to study galaxies and dark matter. When light from distant galaxies passes near massive clusters, it is bent, magnified, or distorted, allowing astronomers to map the invisible matter that causes the effect. In the extreme environment around black holes, gravitational lensing can create multiple images, arcs, and even complete rings of light, known as Einstein rings, around the central darkness. The image of the black hole in M87, captured by the Event Horizon Telescope in 2019, is, in fact, a direct result of such bending. The bright ring is formed by light from the accretion disk being curved almost completely around the black hole, giving us a view of the far side as well as the near side simultaneously. Rotation adds another layer of complexity. A spinning black hole drags space-time around with it in a process called frame dragging, or the lens-thurring effect. This means that objects near a rotating black hole can't remain stationary. They are pulled around in the direction of the spin, even if they try to stay still relative to the stars. The region where this occurs is called the ergosphere, lying just outside the event horizon. Inside the ergosphere, nothing can remain at rest, though escape is still theoretically possible. Frame dragging has been observed around Earth using satellites equipped with gyroscopes, such as the Gravity Probe B mission, which measured the tiny warping of space-time caused by Earth's rotation. Near a black hole, the same effect becomes thousands or millions of times stronger. This twisting of space-time helps power the jets emitted from accreting black holes, channeling magnetic fields and plasma into narrow relativistic beams. All these phenomena, time dilation, redshift, light bending, and frame dragging, are different faces of the same underlying geometry, space-time responding to mass and energy. Each has been verified in one form or another, from laboratory experiments to galactic observations, and each behaves exactly as general relativity predicts. Yet near a black hole's event horizon, these effects grow so intense that they defy normal intuition, turning the familiar notions of distance, time, and motion into something alien. In a sense, black holes serve as the universe's ultimate test chambers for the theory of relativity. Every observation made so far, from the orbital dynamics of stars to the timing of gravitational waves, has confirmed Einstein's equations under conditions of extreme curvature. But they also show us where those equations may one day fail, hinting at the deeper quantum structure of space-time that still waits to be discovered. Black holes are not just isolated gravitational traps. They are central players in the evolution of galaxies, and by extension, the universe itself. Though they occupy a tiny fraction of their host galaxy's total volume, their gravitational and energetic influence extends over tens of thousands of light years. Observations over the past few decades have revealed that nearly every large galaxy contains a supermassive black hole at its center, and that the growth and behavior of those black holes are tightly linked to the formation and evolution of their galaxies. This connection, known as black hole galaxy coevolution, is one of the most important discoveries in modern astrophysics. It emerged from several lines of evidence. In the early 2000s, astronomers found a strong correlation between the mass of a galaxy's central black hole and the properties of its surrounding bulge, particularly the velocity dispersion of its stars. This relationship, called the M-sigma relation, implies that the larger and more massive a galaxy's bulge is, the more massive its central black hole tends to be. The odds of this being a coincidence are extremely low. Some kind of mutual regulation must be occurring. One of the key mechanisms driving this relationship is feedback, the process by which energy released from accretion onto the black hole influences the galaxy's gas and star formation. When a supermassive black hole is actively feeding, it can release more energy than all the stars in its host galaxy combined. This energy is not just emitted as light, but also as high-speed winds, jets, and radiation pressure that can push surrounding gas outward. The impact of this feedback depends on how efficiently the black hole's output couples to its environment. If too much gas is expelled, star formation shuts down, leaving behind a quiescent galaxy populated by old stars. If the feedback is moderate, it can regulate star formation, preventing runaway bursts that would otherwise consume the available gas too quickly. In this way, the black hole acts as both a throttle and a brake, influencing how galaxies grow and evolve over billions of years. Quasars, the luminous active phases of supermassive black holes, provide some of the clearest examples of this feedback in action. Observations with radio and X-ray telescopes have revealed colossal outflows and jets extending hundreds of thousands of light years, hundreds of thousands of miles. These structures can heat the intergalactic medium and drive shock waves through galactic halos. In galaxy clusters where many galaxies share a common envelope of hot gas, jets from a single central black hole can regulate the cooling of that gas, preventing excessive star formation in the cluster's core. This kind of regulation has been observed directly in systems like the Perseus cluster, where cavities carved into the surrounding gas correspond precisely to the paths of radio jets from the central galaxy's black hole. The energy required to create those cavities is enormous, equivalent to the output of trillions of stars over millions of years. Yet the balance it maintains keeps the cluster stable, preventing it from collapsing or overheating. At smaller scales, in individual galaxies, black hole feedback also plays a major role in shaping morphology. Galaxies with actively accreting black holes often display powerful winds that blow gas out of their centers, leading to a decline in new star formation. Over time, this transforms a once blue, star-forming spiral galaxy into a red elliptical one, dominated by older stars. The Milky Way itself appears to be in a transitional stage. Its central black hole, Sagittarius A star, is currently quiet, but there is evidence that it was active in the past. Observations of giant gamma-ray bubbles extending tens of thousands of light years above and below the galactic plane suggest that a past outburst from Sagittarius A star injected enormous energy into the surrounding medium several million years ago. Black holes also influence the dynamics of galactic mergers. When two galaxies collide, their central black holes sink toward the newly formed core through a process known as dynamical friction, where they lose momentum to surrounding stars and gas. As they approach one another, they can trigger intense waves of star formation, starbursts, as gas clouds compress and collapse. Eventually, the two black holes form a binary system, orbiting each other for millions of years before merging in a final burst of gravitational radiation. The merged black hole, now larger and often spinning rapidly, settles at the center of the new galaxy, anchoring its structure. This cycle, formation, feeding, feedback, and merger, repeats throughout cosmic history. Each generation of galaxies and black holes influences the next, establishing a self-regulating ecosystem that governs the large-scale structure of the universe. Without black holes, galaxies would likely look very different. simulations that exclude black hole feedback tend to produce galaxies that are too massive, too dense, and too rich in gas. Only by including the effects of active galactic nuclei do models reproduce the distribution, color, and structure of galaxies observed today. On cosmological scales, black holes may also play a role in distributing heavy elements, magnetic fields, and cosmic rays across intergalactic space. The jets and winds they produce carry material far beyond their host galaxies, enriching the otherwise thin intergalactic medium. This process helps explain why elements like carbon, oxygen, and iron, which are produced in stars, are found in the vast diffuse gas between galaxies. In short, black holes act as engines of cosmic balance. They destroy and create, quench and trigger, shape and sustain. Their presence at the centers of galaxies is not a mere coincidence, but a fundamental component of galactic architecture. They set the tempo of star formation, influence the growth of structure, and may even define the limits of how large or luminous galaxies can become. Despite their reputation as objects of annihilation, black holes are, paradoxically, among the most creative forces in the cosmos. They recycle energy and matter on a galactic scale, weaving gravity, radiation, and motion into patterns that define the visible universe. Supermassive black holes are among the most enigmatic and powerful entities in the universe. Ranging from millions to billions of times the mass of the Sun, they occupy the cores of most large galaxies and act as gravitational anchors around which entire stellar systems evolve. Yet despite their immense influence, these objects likely began as something small. Seed black holes formed in the early epochs of cosmic history, less than 1 billion years after the Big Bang. Understanding how they grew from tiny beginnings to cosmic giants has become one of the central challenges in modern astrophysics. The first hints of supermassive black holes came not from their gravitational effects, but from their extraordinary luminosity. In the 1950s and 1960s, radio telescopes began detecting compact sources of radio waves that had no clear optical counterparts. When astronomers identified some of them with distant points of light, they discovered that these objects, called quasars, short for quasi-stellar, radio sources, were located billions of light years away. Given their brightness, they had to be releasing more energy than entire galaxies, yet their size, inferred from rapid variations in brightness, was smaller than our solar system. The only mechanism capable of producing such enormous energy in such a small volume was accretion onto a supermassive black hole. As matter falls inward, it forms an accretion disk, where gravitational energy is converted into radiation with remarkable efficiency. This process can release up to 10 to 40% of the rest mass of infalling material as energy, depending on the spin of the black hole. For comparison, nuclear fusion in stars converts only about 0.7%. In effect, quasars are natural particle accelerators and power plants operating on cosmic scales. Quasars were initially puzzling because their abundance in the early universe implied that supermassive black holes must have formed very quickly. Observations with modern telescopes, including the James Webb Space Telescope, have revealed quasars existing less than 700 million years after the Big Bang. For a black hole to reach 1 billion solar masses in such a short time, it must either have started from an unusually massive seed or have grown at extraordinary rates, possibly through continuous near-Eddington accretion, where the outward pressure of radiation nearly balances the inward pull of gravity. There are several competing models for how these initial seeds formed. One possibility is that the first generation of massive stars, known as population 3 stars, ended their lives as black holes a few dozen or 100 times the mass of the Sun. Over time, these could merge and accrete to form larger structures. Another possibility is direct collapse, where immense clouds of primordial gas, hundreds of thousands of solar masses in size, collapse directly under their own gravity without fragmenting into stars. This process would create black holes massive enough to serve as the early cores of quasars.